Hi there. Welcome to Certainty YouTube channel, where we make assurance double sure. Changes in temperature produce the expansion or contraction of structural materials, resulting in thermal strains and thermal stresses. When the block is heated, every element of the material undergoes thermal strains in all directions, and consequently the dimensions of the block increase. The change in length can be found by thermal displacement relation, which is alpha change in temperature times length, where alpha is a property of the material called the coefficient of thermal expansion. For most structural materials, thermal strain is proportional to the temperature change. Since we know the relationship between stress and strain, we can come up with a formula to calculate thermal stress. Stress is proportional to strain, where E is the modulus of elasticity. Now, if we substitute thermal strain from the second equation, we can see that thermal stress is equal to alpha change in temperature times E. Now we know that when a solid material is heated or cooled, its length changes. The change in length can be found by multiplying alpha by a change in temperature and the original length of the material. Now we want to look at two examples. The first one is about a simple single bar experiencing a temperature change, and the second one involves composite bars of different thermal expansion rates. Here's the first one. A rod is 2 meters long at a temperature of 0 degrees Celsius. Find the expansion of the rod when the temperature is raised to 70 degrees Celsius. Take E to be equal to 1 times 10 to the power 8 meganewton per square meter and the coefficient of thermal expansion to be equal 0.0000012 per degree Celsius. First of all, let's write down the given data. We are given the length modulus of elasticity, coefficient of thermal expansion, and temperature change. So to find thermal expansion, we use the formula, which is alpha times temperature times length of the material. We have everything from the given data, so it's a matter of substitution. If we do that, we get 0.00168 meters. Take note that we can have a negative temperature change if the temperature drops. Here's the second part of the question. If this expansion is prevented, find the stress induced in the material of the rod. To find thermal stress, we multiply alpha by a change in temperature and E. Remember, alpha is the coefficient of thermal expansion and E is the modulus of elasticity. Let's do that. We know that mega is a unit prefix in metric systems of units denoting a factor of 1 million. Now let's plug in our values, and if we do that, we get our answer as 84,000 newtons per square meter. Of course, we can express this large number in meganewtons. In most cases, the problem won't be easy like the one we solved. We will have statistically determinate and indeterminate structures. A statically determinate structure is one that is stable, and all unknown reactive forces can be determined from the equations of equilibrium alone. A statically indeterminate structure is one that is stable, but contains more unknown forces than available equations of equilibrium. Now let's say we have two materials, the first one is brass and the second one is steel. Since the coefficient of thermal expansion of brass is greater than of steel, when heated, brass will expand more than steel. However, since the two bars are bonded together, the brass bar will have a backward reaction due to steel, and the steel bar force will have a forward reaction due to brass force. Hence, the load or force on the brass will be compressive, whereas on the steel, the load will be tensile. Because the end bars are rigid, the steel bar and brass bar must lengthen by the same amount at the end. To find the resultant stress in each material and the force resisted by each material, we normally use the flexibility method. First, we write the equation for static equilibrium either in the y or x direction. Second, we write the compatibility equation. The equation of compatibility expresses the fact that the net change in length of the composite bars should be the same, or they are fully restrained. Next, we use the force displacement relation to find the increase in the length of the bars due to reaction forces. The formula is force times length over area times modulus elasticity. Finally, we use temperature displacement to find the increase in the length of the bars due to temperature. Now let's look at an example. A bimetallic strip used in a temperature control device is made of stainless steel and brass bonded together as shown. For stainless steel, E equals 193 gigapascal, and the coefficient of thermal expansion equals 16 times 10 to the power -6 per degree Celsius, and for brass equals 103 gigapascal, and the coefficient of thermal expansion equals 19.1 times 10 to the power -6 per degree Celsius. The strip experiences a temperature rise of 20 degrees Celsius. Using the flexibility method, find the force resisted by each material and the resultant stress in each material. We are given a cross-sectional view of the bars, which means we can calculate their respective areas. First, we are going to write the given data starting with the coefficient of thermal expansion for each material. We are also given the modulus of elasticity and temperature. You can see that the length of steel and brass is the same. The area is obtained by multiplying the length by width. You have to take note of units. I want all my units to be in meters, so I'm going to change square millimeters to square meters by multiplying by 10 to the power -6. Like we said before, the strip will expand when heated and the length will increase. Since brass has a higher coefficient of thermal expansion than steel, it will expand fast, hence having a backward reaction, while steel having a forward reaction. Now let's write the equilibrium equation. I am taking the right side as positive. F's minus FBI should give us 0, and if we rewrite F should be equal to FBI. Let's name it equation 1. Next, we write the temperature displacement relation for each material. We use temperature displacement to find the increase in the length of the bars due to temperature. It is wise to not put values at this stage in order to avoid confusion. Let's name these equations 2 and 3. Now let's use the force displacement relation to find the change in the length of bars due to reaction forces. We have the formula, so there is nothing to worry about. The formula is force times length over A times areas. Where is the modulus of elasticity? Let's do that for each material. Lastly, we need to use the compatibility equation. We know that the metallic bars will have the same length and the end of the expansion. Now let's write the equation. The steel bar will increase the length due to temperature and reaction of FBI, while the brass bar will first increase the length due to temperature rise, and then decrease due to the reaction force. If we write this as a statement, this is what we get. Now let's move like terms to one side. We can substitute change in length due to reaction forces with equations 4 and 5, and on the right-hand side, we can factor out change in temperature and length. Since F's and FBI are the same, you can choose what you want, but I will use F's. We said the length is the same for brass and steel, which means we can divide both sides by L. Now let's make the left-hand side a single fraction to simplify our work. Now we can multiply both sides by the denominator and divide by the numerator, and be left with F's on the left-hand side. Now let's substitute everything we have into our formula. If you do that, you should get 124.9 newtons. But Fs equals Fb, so that means we have also calculated Fb. Now let's find the resultant stress in each material. Stress equals force over area. The two bars have same area and same force, so they will have the same stress. Now, let's plug in our values, and if we do that, we get 416333333.3 newtons per square meters. We can express this value in meganewtons if desired, which would be 4.16 meganewtons per square meter.